In the beginning, everything humanity ever built came from the ground beneath its feet. Stone shaped its first shelters, copper and bronze forged its first wars, gold crowned its first kings, and for thousands of years, the pulse of civilization beat in rhythm with the things it could dig from the earth, beneath the glow of cities, beneath oceans and forests. Humanity carved its progress into the planet itself, pulling coal from the dark to light up the night, pulling oil from ancient oceans to drive the age of machines, pulling silicon from sand to weave a world of invisible code. But every step forward left a hollow behind. Every triumph carried a quiet cost that grew heavier with time. The earth is not infinite. Its patience, like its oars, has limits. What was once abundance has become scarcity, veins running dry, oceans acidifying, forests gasping for breath. And yet, demand rises still. The hunger for metals, energy, and data expands like the universe itself. For every smartphone and satellite, for every city of glass and steel, the ground beneath is asked for more than it can give. So now, a strange silence gathers around the question of the future. If the planet that birthed us can no longer sustain our ambition, where does humanity look next? Somewhere beyond the veil of blue sky, in the deep vacuum where no wind blows, mountains of raw creation drift alone. Asteroids, fragments of shattered worlds, frozen and forgotten, circle the sun in endless solitude. Each one is a capsule of the early solar system, a piece of unfinished planet, iron, nickel, platinum, water locked in stone, resources older than Earth itself. Scientists have looked upon these ancient bodies and seen something unsettling, not just relics of cosmic history, but the keys to civilization's next chapter. The numbers defy comprehension. A single metallic asteroid could contain more metal than all that humanity has ever mined since the dawn of industry. In those silent rocks lies the potential to build cities that never run out, engines that never stop, progress that never collapses. But in the same promise hides a darker reflection, because every resource humanity has ever touched, from flint to fossil fuel, has come at a price far greater than its weight. To reach beyond Earth for more might not save us. It might only extend the distance of our hunger. And so, as the planet begins to feel the strain of its own species, the question grows heavier than ever. What if salvation lies not beneath our feet, but beyond the sky? And what if, in reaching for it, we finally learn the true cost of endless progress? Floating silently in the vastness of space, asteroids often appear as little more than specks against the infinite dark. Yet, within their irregular shapes and pitted surfaces lie fragments of a violent past, remnants of worlds that never fully formed. These metallic bodies, composed of iron, nickel, and traces of precious metals, were discovered not as curiosities, but as anomalies, pieces of planetary cores torn from their parent bodies long ago, drifting alone for billions of years. Each one carries the memory of a star system still young in cosmic terms, a frozen record of creation interrupted. The Psyche mission, launched by NASA, seeks to visit one such relic, a massive asteroid believed to be an exposed core of a protoplanet. Unlike the rocky or icy bodies that surround it, Psyche gleams with a metallic luster, a silent testament to processes that shaped entire worlds. For scientists, it is more than a target. It is a window into the interior of planets, offering a glimpse at layers that would otherwise remain hidden beneath crusts and mantles. The very existence of such a body challenges assumptions about planetary formation, suggesting that violent collisions and cosmic disruptions are far more common than once imagined. Spectral analysis has revealed astonishing truths. These asteroids, though small compared to planets, harbor quantities of platinum group metals and other valuable elements that dwarf human production. Billions of tons of metals float freely, bound not by law or economy, but by gravity alone. One body like 16, Psyche, could contain more metal than humanity has extracted in the entirety of its industrial history. A staggering scale that bends the mind, confronting us with the contrast between what is accessible and what remains tantalizingly out of reach. There is an inherent irony in this cosmic abundance. Wealth beyond measure drifts in silence, indifferent to the civilizations that might one day attempt to harvest it. These asteroids are both treasure and enigma, a paradox of possibility. They carry a promise that is simultaneously thrilling and unnerving, an invitation to consider the ambitions and limits of a species still confined to a single world, yet beyond their material value. These bodies are time capsules. Within their metallic hearts lies the history of planetary formation, frozen in forms that predate Earth itself. They record the violence, the chemistry, and the chance that shapes planetary interiors, capturing processes that have sculpted every rocky world in our solar system. In studying them, scientists peer not only into space, but into the origins of worlds, including our own. Each asteroid becomes a narrative of cosmic evolution, a reminder that what seems static is in fact a snapshot of a universe in perpetual motion. And so, as telescopes map their surfaces and spacecraft prepare to touch them, humanity faces a dual revelation: the abundance that exists beyond its reach, and the deep stories these silent wanderers tell. They are fragments of beginnings that never fully blossomed, yet in their quiet orbit around the sun, they hold the potential to rewrite the way we understand wealth, history, and our place in the cosmic order. As the scientific gaze sharpens, it becomes clear that these metallic asteroids are not mere curiosities drifting aimlessly in space. They are monuments to the chaotic adolescence of our solar system, formed from violent collisions that shattered embryonic planets. These fragments offer a raw, unaltered glimpse into the forces that shape worlds. Unlike Earth, whose layers have been folded, eroded, and reformed over billions of years, these bodies remain pristine, a record untouched by tectonics, atmosphere, or biosphere. The metals embedded within them, iron, nickel, and traces of platinum, osmium, and iridium, were forged in the cores of stars, transported across eons, and finally locked within these wandering shards. In their existence lies both the poetry and the precision of cosmic evolution, chaotic destruction producing ordered treasure, a contradiction mirrored in the human imagination. NASA's Psyche mission, when it reaches its target, will illuminate not only composition but structure, revealing whether the asteroid is a solid metallic heart or a fractured core held together by gravity. High-resolution mapping and spectroscopy will uncover subtle variations in mineralogy, exposing patterns that hint at cooling rates, magnetic fields, and the violent collisional history that carved it into shape. Scientists speculate that these data could redefine the understanding of planetary differentiation, shedding light on how Earth's own iron core coalesced, generating the magnetic field that shields life. The asteroid becomes more than a body of metal. It becomes a bridge between past and present, between what has formed naturally and what might be harnessed deliberately. The sheer scale of material raises questions that extend beyond science into the domain of philosophy and ethics. To consider one asteroid's mass billions of tons of platinum group metals is to confront the absurdity of cosmic abundance. Humanity's terrestrial economies have been shaped by scarcity, by the uneven distribution of resources that created value ambition, and conflict. Yet here lies an entire world whose mineral wealth dwarfs all that has been extracted from Earth since civilization began. The possibility of accessing even a fraction of such wealth provokes both exhilaration and unease. What would it mean to suddenly possess resources that challenge centuries of economic order? Could abundance in the void recalibrate notions of worth, of progress, and of human aspiration itself? Beyond material considerations, these asteroids are laboratories of planetary science. Their surfaces may preserve clues to early magnetic fields, to the composition of protoplanetary disks, and to the dynamics of collisions that prevented them from forming larger planets. Each crater, fissure, or metallic seam tells a story, waiting for human ingenuity to interpret it. Robotic probes might extract tiny fragments, analyze them in orbit, and beam data back to Earth, allowing scientists to reconstruct the violent, fragmented dance that shaped our neighborhood of stars. In doing so, humanity learns not just about asteroids, but about the processes that created Earth, that allowed water to accumulate, and that set the stage for life itself. Yet, even in the midst of such scientific potential, there is a lingering tension. The knowledge of these silent giants' abundance is accompanied by an awareness of their elusiveness. Unlike rivers, mines, or forests, these objects float in a vacuum hundreds of millions of kilometers away, accessible only through ingenuity, risk, and extraordinary expenditure of energy. Their wealth cannot be claimed by mere desire. It demands mastery of physics, robotics, and orbital mechanics. The poetic irony persists. The universe offers its bounty freely, yet not without exacting effort, and in that effort, humanity confronts its limitations as well as its ambitions. As astronomers, engineers, and dreamers focus telescopes, design spacecraft, and model extraction techniques, a subtle revelation takes shape. These asteroids are not just resources, but mirrors. They reflect the scale of the universe, the intricacies of formation, and the audacity of human curiosity. In contemplating them, the line between science and speculation blurs, and the imagination stretches to meet the vastness of space. Each metallic fragment becomes a narrative of possibility, a silent challenge posed by the cosmos, to understand, to reach, and perhaps to reshape the destiny of civilization itself. Amid the silent drift of asteroids through the void, a subtle but profound question emerges, one that extends beyond mineral composition and spacecraft trajectories. What is wealth when measured against the cosmos itself? On Earth, value has always been dictated by scarcity. Gold gleamed because it was rare. Platinum sparked industries because it was difficult to claim. Yet in the expanse of the solar system, scarcity is an illusion. The stars and the fragments that circle them do not obey human notions of limitation. A single asteroid, rich in metals, has the theoretical potential to exceed the sum of every mine, every refinery, every vault on Earth. Its existence challenges the very framework through which humanity has understood economy, property, and progress. Early simulations conducted by planetary economists and systems theorists paint a striking vision, introducing even modest quantities of extraterrestrial metals into terrestrial markets could destabilize centuries of economic order. Inflation, deflation, and the collapse of commodity value intertwine in complex feedback loops, revealing how tightly human society is bound to the scarcity of the planet itself. The very wealth that has driven civilization, the tools, the cities, the networks, relies upon artificial limitations. And in the presence of cosmic abundance, those limitations vanish, leaving civilization to confront the paradox of its own creation, wealth without bounds, but value rendered uncertain as astrophysicists map orbital paths and mineral densities. Attention arises with economists who ponder ownership and rights. What does it mean to own a piece of rock drifting hundreds of millions of kilometers from Earth? The Outer Space Treaty prohibits sovereign claims over celestial bodies, yet allows utilization of resources. Suddenly, the cosmos becomes a landscape not only of scientific curiosity, but also of legal and moral ambiguity. Can wealth exist independently of governance? Does the act of extraction constitute ownership or merely stewardship? Every calculation becomes an ethical as well as a financial exercise, and the boundaries of law, philosophy, and human ambition blur. From this tension, a new discipline emerges: space economics, a theoretical framework attempting to reconcile physics with finance, gravity with governance. Researchers construct models for resource allocation in the vacuum, exploring how material could be distributed without national appropriation, how trade might function beyond planetary borders, how technology could mediate access. These models suggest futures both exhilarating and perilous: a civilization enriched beyond imagination, or one fractured by the inequities of interstellar resource control. The specter of a cosmic gold rush looms large. In private sector labs and university think tanks, engineers and financiers imagine fleets of mining drones, autonomous harvesters, and orbital refineries racing toward untapped asteroids. Yet with opportunity comes ethical tension. Extracting without reflection risks replicating historical patterns of exploitation, extending Earth's conflicts into the heavens. Profit, technology, and survival become entwined, and every decision resonates far beyond the boundaries of immediate gain. And yet, as the models and simulations converge, a deeper understanding crystallizes. This is not merely a story about metals. It is a story about control over the future of civilization, over the trajectory of human ambition, over the rhythm of progress itself. In the silent orbits of these ancient bodies, a question hovers that is as philosophical as it is material. Who will shape the destiny of wealth in the cosmos? And by extension, who will shape the destiny of humanity? In this quiet reflection, the mystery deepens, and the vastness of space becomes a mirror, reflecting the ambitions, fears, and hopes of a species poised to step beyond its terrestrial cradle. The paradox of cosmic wealth grows more profound when considered alongside the limits of human perception and imagination. On Earth, scarcity has always given structure to society. It defines markets, shapes hierarchies, and motivates exploration. Yet in space, abundance is untethered from these familiar constraints. A single asteroid can contain more platinum than has been mined across all human history, more water than many nations can store, and iron sufficient to build entire cities in orbit. The scale is incomprehensible, defying intuition, and yet it exists in silence, indifferent to human desire. This abundance forces a confrontation with the idea that value is not intrinsic. It is relational, defined by access, risk, and societal context. Without scarcity, the very notion of wealth becomes fragile, dependent not on what exists, but on who can reach it and under what conditions. Economic theorists have begun to model these scenarios, employing simulations that treat entire planetary markets as dynamic, elastic systems. In these models, introducing hundreds of tons of cosmic metal could trigger cascading effects. Commodity prices would plummet, industries dependent on scarcity would falter, and nations reliant on extractive economies could face destabilization. Yet these projections are more than financial exercises. They are philosophical explorations of how humanity might adapt to a universe where limits are no longer imposed by geography, but by ingenuity. The tension between potential and feasibility is acute. The resource is abundant, yet extraction is costly, risky, and technically daunting. Every calculation, every simulation, balances the promise of transformation against the reality of limitation. The interplay between economics and physics becomes starkly tangible when ownership is considered. The Outer Space Treaty and subsequent international agreements prohibit sovereign claims on celestial bodies, yet they allow the use of resources. Here law meets the vacuum, and ethics confront opportunity. Does possession require proximity? Must wealth be tangible to have meaning? Asteroid mining challenges these assumptions, compelling humanity to rethink not only property but responsibility. Legal scholars, ethicists, and scientists converge in a dialogue as speculative as it is practical, wrestling with questions that will define the next century: how to ensure equitable access, how to prevent exploitation on a cosmic scale, and how to measure value when it is no longer rooted in limitation. Meanwhile, space economics evolves as a discipline, drawing from astrophysics, finance, and game theory. Models explore autonomous mining fleets navigating orbital highways, automated resource processing in microgravity, and distribution networks linking Earth to orbital refineries. These scenarios are not merely theoretical, they are the blueprint for a future in which humanity may finally escape terrestrial scarcity. Yet within these models lies a cautionary undertone. Abundance without foresight can be as destabilizing as deprivation. The distribution of wealth becomes inseparable from the governance of access, the ethics of extraction, and the foresight to balance growth with sustainability. The prospect of a cosmic gold rush is more than a metaphor. It is a looming reality. Private companies envision fleets of autonomous craft racing silently toward asteroids laden with metals and water. Universities and government agencies study the orbital mechanics, extraction techniques, and energy requirements with painstaking care. The potential is exhilarating, yet each step forward illuminates ethical and philosophical dilemmas. Mining a celestial body is not merely a technical challenge, it is a statement about humanity's relationship with the universe. It asks whether ambition will be guided by prudence or unchecked desire, whether progress can coexist with reflection. Ultimately, the mystery deepens because this is no longer a question of material gain alone. It is a question of influence, foresight, and the shaping of civilization's trajectory. Control over cosmic resources may determine the balance of power, the direction of technology, and even the fate of economies on Earth. In the quiet drift of asteroids through the void, one perceives a subtle truth. Wealth in the cosmos is inseparable from choice, and choice carries responsibility, risk, and consequence on scales that stretch across millions of kilometers and billions of years. Humanity stands at the threshold, confronted by abundance that challenges not only understanding, but the very meaning of value itself. In that confrontation, the mystery endures, vast, silent, and profoundly transformative, long before telescopes pierced the night sky, before spacecraft traced silent arcs through the void. Humanity looked upward and imagined the heavens not as distant emptiness, but as a source of wonder and of wealth. Ancient myths spoke of metals falling from the stars, celestial gifts forged in fire, carried to earth by divine will. Iron from meteorites was revered, sometimes worshipped, sometimes wielded in ritual or in war, its otherworldly origin lending it a power that transcended earthly matter. These stories, suspended between awe and aspiration, were the first whispers of a desire that would one day stretch beyond myth and into the realm of science. By the mid-20th century, imagination had become engineering. The Apollo missions of the 1960s carried humanity's curiosity into the vacuum itself, returning with fragments of the moon rocks, imbued with isotopes and minerals that Earth had never seen. These were more than geological samples. They were revelations. Each fragment bore silent testimony to processes that had shaped not only our satellite, but the solar system itself. Water trapped in regolith, traces of rare metals, isotopic ratios that told stories of cosmic history. These discoveries were the first hints that the materials of life and civilization might exist beyond Earth, waiting to be understood, perhaps even harnessed. The same period saw the Cold War transform the night sky into a stage for human ambition. Rockets carried more than instruments and flags. They carried the implicit notion that space was not just a place to explore, but a place to claim, to utilize, and eventually to extract. The dual forces of scientific curiosity and geopolitical competition nurtured an idea that had lain dormant for centuries. The universe itself might be a repository of resources, a vast treasury orbiting the sun, awaiting the ingenuity of humankind. It was not until the 1990s, however, that systematic observation of the near-Earth environment began to reveal the scale of opportunity. Astronomers, using increasingly sophisticated telescopes and surveys, mapped countless small bodies, noting compositions and orbits with unprecedented precision. These were not mere hazards to navigation or objects of study, they were potential mines, drifting repositories of iron, nickel, platinum, and water. The realization that these bodies could be accessible, even if only in principle, transformed the cosmic imagination from abstract wonder into tangible possibility. In the early 21st century, the private sector embraced what had long been speculative science. Companies like Planetary Resources and Deep Space Industries imagined fleets of spacecraft harvesting metals from orbiting rocks, transforming science fiction into plans, prototypes, and business models. The idea of commercial off-world mining, once relegated to novels, became a concrete ambition. Engineers and entrepreneurs sought to touch the material promises of the void, driven by the same human urge that had built cathedrals atop hills, laid railroads across continents, and bridged oceans with steel. Beneath the technical detail and commercial aspiration, there lies an emotional core, the desire to reach beyond the familiar, to turn imagination into reality, is as old as humanity itself. The same curiosity that prompted early astronomers to chart the stars now fuels robotic explorers, survey telescopes, and daring entrepreneurs. What was once the subject of legend and myth has become the focus of mission plans and orbital projections. The yearning for resources beyond Earth is ultimately a reflection of a deeper impulse, the urge to extend human presence, to touch the unknown, and to shape the destiny of civilization upon a canvas larger than any planet. In these stories, the cosmos is not only a frontier of matter, it is a mirror, reflecting the persistence, ambition, and audacity that define our species. As these early visions evolved, a subtle yet profound shift took place in the way humanity conceived of space. No longer was it simply a theater for scientific inquiry or national prestige. It became a domain in which the boundaries of industry, law, and ambition might converge. The moon rocks, brought home by Apollo, were studied in laboratories, their mineral content meticulously catalogued, but they also stirred something less tangible, a recognition that the cosmos was not only a stage for exploration, but a repository of material wealth, a silent archive of resources that had never known the weight of human hands. It was a realization that would seed decades of speculation. eventually crystallizing into plans for extraction and utilization. By the 1990s, the combination of improved observational technology and computational modeling allowed astronomers to categorize near-Earth objects with unprecedented accuracy. Surveys such as Linear and NEAT catalogued thousands of asteroids, charting their orbits, sizes, and compositions. Some were carbonaceous, rich in water and organic molecules. Others were metallic, containing concentrations of nickel, iron, and platinum group elements that exceeded terrestrial reserves. For the first time, humanity could imagine not only reaching these bodies, but understanding their potential value in quantitative terms. These observations transformed space from a distant curiosity into a prospective source of tangible resources. And with that transformation came new questions about economics, governance, and ethics. The private sector's engagement marked a new chapter in the story, blending ingenuity with ambition. Planetary Resources, founded in the late 2000s, articulated a vision that combined space science with industrial strategy. Autonomous spacecraft would prospect, survey, and eventually extract metals from near-Earth asteroids. Deep space industries pursued similar goals, developing technology concepts for in-orbit processing and transport. While the technical challenges were enormous: microgravity drilling, energy-efficient propulsion, and resource capture in a vacuum, the conceptual leap was perhaps even greater. The notion that wealth, historically anchored to Earth, could now be projected into space. These companies represented not just entrepreneurial daring, but the culmination of millennia of human aspiration, reframed for a cosmic scale. Underlying these developments was a continuity of human desire that stretches back to the earliest civilizations. Just as empires mined mountains for gold to assert power, just as pioneers carved railways across continents to claim and connect, humanity now casts its ambitions toward celestial bodies. The same curiosity that drove early astronomers to chart comets and meteor showers now fuels the design of robotic prospector fleets and orbital mining platforms. There is a poetic symmetry in this continuity, from hand-wrought metal to orbital foundries, from mythic reverence of star metal to calculated extraction. The impulse remains the same, yearning to reach beyond, to convert observation into influence, to harness nature in service of progress. Yet the emotional resonance of this story is not solely in ambition or achievement. It lies in the interplay of risk and wonder. Every mission, every proposal to touch the void, confronts the vastness of space and the fragility of human effort. The cosmos is indifferent, its rewards not guaranteed, its challenges unyielding. Each asteroid surveyed, each moon fragment analyzed, is both a promise and a reminder that opportunity exists only within the parameters of knowledge, preparation, and imagination. The narrative of discovery is inseparable from the narrative of restraint, and within this tension, a philosophical depth emerges. In contemplating the trajectory from ancient myth to robotic spacecraft, one perceives the full arc of human ambition refracted against the backdrop of the solar system. The stars and their fragments are more than objects. They are symbols, reflecting the persistent curiosity, daring, and hope of a species striving to transcend its terrestrial bounds. Humanity's first encounters with cosmic material through myth, through Apollo, through asteroid surveys, were not isolated events, but layers in a continuum. Each step has carried us closer to the possibility of not merely observing, but participating in the economy of the cosmos, transforming the celestial into the tangible. In this, the emotional and philosophical heart of the story emerges. The desire to touch the heavens is inseparable from the desire to understand ourselves. and to recognize that every act of extraction carries consequences as vast as the void itself. In the quiet expanse between planets, a tension begins to take shape, a subtle, almost imperceptible conflict, yet one that may define the future of human ambition. On one side are the dreamers, visionaries who see asteroids and metallic fragments not as inert rocks, but as gateways to civilization's next chapter. They imagine robotic fleets harvesting platinum, water, and iron, powering industries that could extend humanity's reach beyond Earth, enabling colonies on Mars and orbital cities bathed in perpetual sunlight. For them, the cosmos is not simply a stage for observation, but a canvas for creation, a frontier where ingenuity can flourish, unbound by terrestrial limits. Yet opposing this fervor are the protectors, conservationists, ethicists, and cautious scientists who regard these celestial bodies as part of a larger cosmic heritage, relics of planetary formation preserved over billions of years. To exploit them, they argue, is to repeat the mistakes that scarred Earth's extraction without reflection, ambition without foresight. They see the silvery glint of metals not as promise, but as peril, a warning that the same impulse which fueled empires, industrial revolutions, and environmental collapse could extend into the heavens, carrying ruin into domains that have remained untouched since the birth of the solar system. Between these perspectives lies a profound dilemma, mirrored in the very instruments humanity sends to touch the void. Engineers confront impossible physics, microgravity that resists leverage, vacuum that strips away heat and mass, orbits that demand precise timing, and robotic systems that must act autonomously across millions of kilometers. Every mission is a negotiation between human intent and cosmic indifference, a reflection of our species' capacity to shape or to stumble in the universe. And yet, even as technology advances, the moral questions persist. Are these asteroids part of a natural order that must remain inviolate, or are they abandoned remnants, available for the taking by those who dare? The answer is not obvious, and the very act of questioning it reveals a species still learning its place in the cosmos. The conflict is not solely philosophical. It is embedded in the human experience of curiosity itself. Scientists, whose curiosity drives them to touch new worlds, often feel a tension between discovery and responsibility. Each sample returned, each mineral analyzed, carries the weight of potential impact, both material and ethical. The act of studying these bodies becomes inseparable from the act of claiming them, and the boundary between knowledge and exploitation blurs. Every mission becomes a mirror, reflecting not only the ingenuity of its creators, but also the priorities, fears, and values of the civilization that sent it. In this tension, there is an emotional resonance that transcends economics or engineering. The dreamers and the protectors are, in essence, two sides of the same consciousness, one reaching outward, propelled by ambition, the other looking inward, constrained by reflection and caution. Together, they define the moral and philosophical landscape of space exploration, where every decision echoes across vast distances and eons. Humanity's reflection emerges in the machines it builds, in the probes that drift silently among stars, and in the choices yet to be made about what to take, what to leave, and what it truly means to reach beyond one's home. The story of discovery, then, is inseparable from the story of conflict, internal, ethical, and profound. In the gleaming surface of a metallic asteroid, in the silent drift of a regolith-laden fragment through the void, humanity confronts itself, its ambition, its responsibility, and its capacity for foresight. The cosmos becomes both opportunity and conscience, and in this mirror, the dreamers and protectors meet. shaping not only the future of resources, but the very character of the species daring to reach beyond its cradle. The rift between visionaries and protectors is more than abstract. It manifests in every decision about how to approach the void. Space agencies weigh missions not only for scientific return, but for the broader ethical consequences of touching what has remained untouched for billions of years. Each asteroid mapped and catalogued is more than data. It is a choice, a step along a moral continuum. If humanity decides to mine one of these bodies, it risks establishing a precedent that the vacuum of space is not sacred, but a frontier to be claimed and consumed. And yet, hesitation carries its own weight. Every delay allows opportunity. To drift by, every cautious study may mean that the first hands on a metallic asteroid are those guided solely by profit, not reflection. Engineers face daily reminders of human limitations against cosmic scale. In microgravity, even the simplest motions become complex, every grasp an extraction, a negotiation with physics itself. Robotic arms must anchor to surfaces that offer no resistance. Drills must bite into rock without gravity to hold debris in place. And propulsion systems must counter the slightest nudge, lest the entire operation drift into space. The machines themselves become extensions of human ambition, but also of human fallibility. In their precision and fragility, they echo the broader tension of discovery. Every advance is contingent on skill, patience, and understanding, yet the stakes of failure stretch far beyond any laboratory. Beneath technical hurdles lies a deeper, almost philosophical layer. Humanity's relationship with these asteroids forces a reckoning. Are these fragments merely raw materials awaiting use? Or are they cosmic artifacts, records of planetary evolution that deserve preservation? Environmentalists and ethicists argue that the impulse to extract is not neutral. It carries the imprint of Earth's history, of industrial revolutions and ecological collapses. To extend that impulse into space is to risk repeating mistakes on a larger scale, to turn pristine relics into commodities before their stories are fully understood. In this sense, mining is not simply an economic act, but a moral one, a declaration about how a civilization values the cosmos relative to itself. Yet, the pull of ambition is irresistible. The dreamers see opportunity, hope, and progress entwined in the metallic sheen of distant asteroids. They envision industries powered by abundant resources, spacecraft fueled by water extracted from ice-laden bodies, construction materials delivered to orbiting habitats. For them, hesitation is a luxury, and the vacuum of space is a canvas on which to project the next era of human achievement. But their excitement is tempered by awareness of the scale of risk, not just the technical, but the ethical. Every choice made in extraction and design carries consequences that may ripple across decades, affecting economies, societies, and the trajectory of civilization itself. In the tension between these perspectives, a reflection of humanity emerges. Each mission, each robotic probe, and each orbital survey becomes a mirror, revealing collective hopes, fears, and ethical frameworks. The dreamers and protectors are inseparable, two aspects of the same consciousness, the urge to create and the impulse to reflect, the desire to seize opportunity and the caution born of experience. In observing the asteroids and contemplating their use, humanity observes itself, its capacity for ingenuity, for foresight, and for restraint. The void, silent and indifferent, forces confrontation not only with the universe, but with the nature of ambition and the ethics of progress. Ultimately, this is a story of choice. In every orbit, every landing attempt, every sample taken or left untouched, humanity is called to define who it wishes to be. The asteroids, ancient and unyielding, bear witness to these decisions. They are not passive objects, but ethical landscapes, silent arbiters of ambition. And in navigating them, in negotiating the tension between exploitation and preservation, dreamers and protectors alike contribute to a narrative that will define not only the future of space mining, but the character of the species reaching ever outward into the cosmos. In the silent reaches between Earth and Mars, humanity began to extend its reach, not with grand edifices or sweeping colonization, but with subtle, precise gestures, tiny probes touching worlds that had never felt the presence of living things. NASA's OSIRIS-REx and Japan's Hayabusa, too, became the first emissaries of this effort. Spacecraft designed not merely to observe, but to interact, to collect, to return a fragment of the untouchable. These missions marked a profound shift. The cosmos was no longer an abstract domain of distant observation, but a material landscape that could, in small but significant ways, be experienced, studied, and brought home. Landing on a body with barely a whisper of gravity is an endeavor that defies intuition. Asteroids spin slowly, irregularly, their surfaces pocked with craters and loose regolith that drifts at the slightest disturbance. Every maneuver demands exquisite precision. A thrusters burn too long, and the probe drifts past its target. Too short, and it may rebound into space, leaving a faint imprint of human effort on an unyielding surface. Engineers liken it to touching a balloon suspended in the wind, yet with stakes measured not in lost air, but in the culmination of decades of research, technology, and planning. Every second is a negotiation with physics itself. Every contact, a dialogue between human intent and the universe's indifference. When the samples finally returned to Earth, they carried more than minerals. Microscopic grains of rock, some smaller than a single grain of sand, preserved the history of the solar system in their crystalline structures. Within them were clues to the processes that formed planets, to the collisions that shaped worlds, to the primordial chemistry that seeded water and organic compounds throughout the cosmos. Scientists peered through electron microscopes and spectrometers, reading stories written over billions of years, realizing that in these tiny fragments lay evidence of events far older than humanity itself. These grains became a bridge between the vastness of space and the intimacy of human understanding, each particle a testament to the subtlety and persistence of curiosity. Parallel to these missions, private ventures began to test the boundaries of in-space operations. Microsatellites and small-scale prototypes experimented with orbital extraction, with autonomous collection of material, with the beginnings of manufacturing in zero gravity. 3D printing with off-world matter, once the realm of speculation, became a laboratory reality. Even in the absence of industrial-scale mining, these experiments demonstrated the potential to manipulate and utilize cosmic resources directly, hinting at a future where construction, fuel generation, and life support might be sustained by materials that never touched Earth. One of the most transformative discoveries emerged unexpectedly: water, locked within asteroids, abundant in forms both hydrated and frozen. This revelation carried profound implications. Water is not merely a substance. It is a foundation for propulsion, for life support, for sustaining human presence beyond the cradle of Earth. The realization that asteroids could serve as cosmic reservoirs reframed the entire concept of exploration. Humanity need not haul every resource from home, but could refuel, hydrate, and build amidst the stars themselves, in the microscopic grains and ice-laden rocks. A subtle revolution had already begun. It became clear that space mining was not a distant dream, but a process already underway, unfolding slowly, deliberately, in measured steps. Every sample collected, every test conducted, every prototype launched into orbit was a proof of concept, a quiet assertion that humanity could interact with the cosmos without annihilating it, that the untouchable could, with care and ingenuity, be touched. And in this recognition, the narrative shifted. The story of extraction is inseparable from the story of understanding, and the first gestures toward cosmic utilization are as much a reflection of human patience and precision as they are of ambition. In these early investigations, the universe whispered its possibilities, a landscape where knowledge and resource converge, where microscopic grains reveal billions of years, and where the first tentative acts of mining are already shaping a civilization reaching beyond its home. Humanity's presence in space, delicate yet deliberate, becomes a mirror of what it means to aspire without destruction, to touch without consuming, and to transform curiosity into responsibility. The untouchable has been touched, and with that touch, the first chapter of cosmic industry quietly begins. Even as these missions returned their treasures to Earth, the lessons they offered extended far beyond laboratory analysis. Each sample became a tangible proof of concept, a demonstration that humanity could not only reach the void, but interact with it in meaningful ways. The sheer precision required to collect even milligrams of material underscored the difficulty of cosmic work, revealing that mining in space is less a matter of brute force and more a delicate choreography between engineering, orbital mechanics, and patience. Scientists and engineers began to see asteroids not as passive rocks, but as partners in a subtle dialogue, responding to human ingenuity while reminding explorers of their limits. The discovery of water within these small bodies transformed the conceptual landscape entirely. Water, previously assumed to be rare outside comets and icy moons, appeared in unexpected abundance within carbon-rich asteroids. This revelation suggested the possibility of in situ resource utilization using local materials to sustain spacecraft, produce fuel, and even support habitats in orbit or on distant worlds. The implications were staggering. Missions no longer needed to carry every drop of propellant from Earth, and human presence beyond the planet became technically and economically feasible in ways that had once existed only in theory. In these icy veins, the universe offered not only matter, but autonomy, a means for humanity to extend its reach without tethering itself entirely to terrestrial supply chains. Simultaneously, private and government initiatives began experimenting with the mechanics of extraction. Microprobes, designed to anchor themselves to asteroid surfaces, tested methods of surface collection, regolith manipulation, and even small-scale heating to release trapped volatiles. Engineers observed how dust responded in microgravity, how tiny jets of gas could shift debris, and how autonomous systems might operate in environments with no atmosphere to moderate motion. Each trial, each failure, became a lesson in adaptation, revealing the subtle physics of worlds whose behaviors defied intuition. The cosmos, in this way, became a classroom, where patience, observation, and precision were rewarded more than speed or force. Beyond the physical and technical challenges lay an equally profound philosophical revelation. Every asteroid touched, every grain returned, forced humanity to confront the reality of its influence. These bodies, billions of years old, had drifted through the solar system untouched, preserving chemical histories and structural secrets. By interacting with them, even gently, humanity began to participate in a process that had once been entirely natural. The act of collection, though small, carried weight, not only materially, but symbolically. It was a quiet assertion that civilization could extend its presence beyond Earth without erasing the record of cosmic history. A balance between curiosity and stewardship, ambition and respect. With these early missions, a new cadence of discovery emerged, one that combined science, ethics, and engineering in a single, continuous narrative. The tiny quantities of material returned, the delicate operations of microprobes, and the careful observation of water and minerals all signaled that humanity was already mining space. Though in slow, measured gestures, the frontier was not a distant goal. It was an ongoing process, unfolding in laboratories, control rooms, and orbiting spacecraft. And within this process, the profound realization took hold. Every grain of asteroid material brought home is a reminder that exploration and utilization are intertwined, that understanding precedes extraction, and that the cosmos responds to both ambition and respect in equal measure. Ultimately, the first touch of the untouchable reshaped the imagination. The act of returning cosmic material to Earth demonstrated that the universe could be approached, studied, and, eventually, used in ways that had once been purely speculative. The boundaries between science fiction and reality blurred, yet the endeavor retained a quiet, deliberate elegance. Humanity was beginning not just to observe, but to participate in the solar system's material story. Each mission became a meditation on precision, patience, and responsibility, and through these early investigations, the contours of a new era where space mining might become routine were already emerging in the delicate interplay between human ambition and the infinite silence of the void, at the edge of the known and the possible. Human ingenuity confronts a realm where the rules of Earth no longer apply. In microgravity, the very act of movement becomes a negotiation with physics. A simple push against a rock sends both miner and material drifting in opposite directions, the absence of leverage demanding new approaches, new ways of thinking about force, friction, and motion. Heat disperses differently, dust behaves unpredictably, and the vacuum itself becomes a medium that challenges intuition. Engineers confront these realities not through imagination alone, but through simulations, laboratory tests, and carefully orchestrated microgravity experiments. Every discovery, every adjustment, extends the frontier of what is technically possible, revealing the subtle, unforgiving elegance of the void. Traditional mining methods, drills, excavators, and conveyors, are ill-suited to this environment. Microgravity demands innovation, a rethinking of both tools and strategy. Robotic systems must anchor themselves to irregular surfaces, absorb recoil, and operate autonomously when communication delays make direct control impossible. Dust, fine and pervasive, threatens instruments, optics, and propulsion, and behaves with a quiet chaos, floating in unpredictable arcs and reflecting light in ways that confuse sensors. Each challenge forces engineers to translate decades of terrestrial knowledge into a language compatible with the physics of space, creating machines that are part mechanic, part algorithm, and part adaptive intelligence. Emerging concepts stretch the imagination further. Autonomous swarms of AI-controlled drones, each coordinating with the others through near-instantaneous calculations, could sweep over an asteroid, identifying rich deposits and extracting material without a single tethered hand. Laser ablation, a method of vaporizing rock from a distance, might allow for contactless collection, converting solids into vapors that are then condensed and harvested. These theoretical technologies speak not only to efficiency, but to a poetic vision that the void itself can be harnessed. that matter and energy can be manipulated without violating the fragile equilibrium of orbit and inertia. In this frontier, thought and machine merge, and the boundary between human ambition and technological realization becomes nearly imperceptible. Transporting material back to Earth presents its own extremes. Each kilogram demands immense energy to escape the asteroid's orbit, to reach the delicate gravitational corridor that leads home. Delta V, the measure of velocity change, becomes currency, costing millions for every handful of matter. These logistical constraints force planners to consider alternatives, refining and manufacturing in situ, using the asteroid itself as the source of structural material for orbital habitats, or generating fuel from water ice extracted on-site. The concept of insight to resource utilization transforms the challenge from simple extraction into the creation of an entirely new industrial ecosystem, one that thrives in the vacuum rather than fighting against it. In this vision, the cosmos is no longer a passive backdrop. Rock and vacuum, sunlight and orbital paths become the raw materials for civilization. Factories orbit in silent arcs, powered by energy harvested directly from the sun, converting mineral-rich fragments into structures, fuel, and even life support systems. The poetic resonance of this image is profound. Humanity, long bound to the surface of a single world, begins to weave its presence across space, turning obstacles into opportunity, emptiness into infrastructure, and isolation into enterprise. At the extreme edge of science, ambition is measured not only in speed or scale, but in understanding. Each algorithm, each mechanical innovation, each theoretical design is a testament to humanity's ability to adapt, to translate terrestrial knowledge into the language of the void. And yet, the endeavor is quietly humbling. For every advance, the cosmos reminds explorers of its indifference, its scale, and the precision required to survive and to create. In these delicate balances, engineering becomes philosophy, labor becomes meditation, and the act of mining is transformed into an exploration of possibility itself. The void, indifferent yet abundant, becomes a canvas. Here, sunlight illuminates the metallic sheen of distant fragments. Robotic arms etch patterns into regolith, untouched for billions of years, and the potential for life, industry, and knowledge emerges directly from the silence. In this extreme environment, where gravity is fleeting and matter behaves in strange, elegant ways, humanity discovers not just the mechanics of extraction, but the contours of its own ambition, its capacity for patience, foresight, and imagination stretch to the limits of physics itself. Beyond the mechanics of extraction lies the subtle artistry of efficiency, where every motion, every photon of energy must be carefully orchestrated. In the vacuum, sunlight itself becomes a tooler source of power, a vector for propulsion, and, in some concepts, even a means to manipulate surface material through focused energy beams. Engineers and physicists model the delicate interplay between radiation pressure, thermal conduction, and particle dynamics, seeking methods to move matter without disturbing the fragile equilibrium of orbit. Here, science is not only practical, it becomes poetic. A beam of concentrated light can vaporize metal from a rotating asteroid, shaping both its surface and the trajectory of resources, while leaving the surrounding environment nearly untouched. Each operation reads like a quiet choreography between intention and natural law, a testament to human ingenuity operating within cosmic constraints. Robotic swarms, networked and autonomous, represent the next evolution of this extreme engineering. Individually, each unit is limited, capable of small manipulations, precise observations, or minor adjustments. Together, however, they form an intelligent collective, coordinating in real time, adapting to unforeseen conditions, and optimizing every action for maximum yield. In this model, the machinery itself embodies a form of distributed cognition, a reflection of human planning extended into the vacuum. The swarm moves as though alive, a delicate dance over surfaces that were once considered untouchable. And in their coordination, one glimpses the potential for a new type of industry, where intelligence and precision replace brute force, and every action is informed by both physics and foresight. The question of scale becomes unavoidable. Even the smallest metallic asteroid may contain more valuable resources than have been extracted throughout human history, yet to access them requires not only technical mastery, but also profound logistical planning. Transporting material back to Earth is not merely a matter of speed. It is a negotiation with the energy costs of moving mass across millions of kilometers, with orbital mechanics dictating when and how resources may be moved most efficiently. In situ utilization emerges not as an alternative, but as a necessity. By refining metals, producing fuel, and even fabricating components directly in orbit, humanity begins to conceptualize a civilization that is partially untethered from the planet's surface, a civilization where the void itself participates in production. This vision carries a distinct aesthetic, one that is at once industrial and sublime. Orbital factories glint in the sunlight, their surfaces reflecting the stark blackness of space. They are composed of asteroidal iron and silicates, transformed through laser melting, additive manufacturing, and robotic assembly into structures that support further exploration. Solar arrays stretch like wings into the void, capturing energy that drives both machinery and life support. In this image, humanity has not conquered space in the traditional sense. It has learned to work with it, to shape it without dominating it, to translate cosmic resources into infrastructure without destroying the environment that nurtured them for billions of years. At its heart, the engineering of the void is a meditation on limits. Every design, every maneuver, every theoretical model confronts the absence of gravity, the scarcity of energy, and the unpredictability of microscale physics. Yet within these constraints, creativity flourishes. The vacuum becomes a laboratory, the asteroid a workshop, and sunlight both tool and companion. Humanity's presence, fragile and deliberate, illuminates a new paradigm, that progress in space is not measured solely by extraction, but by the elegance and care with which it is executed. Ultimately, the extreme edge of science reveals a profound truth that in mastering the mechanics of the cosmos, humanity also discovers its own capacity for patience, precision, and reflection. The machinery, algorithms, and processes that operate among drifting asteroids are more than technological marvels. They are expressions of an ambition tempered by understanding, a civilization learning to extend its reach without collapsing under its own weight. In the cold, silent void, where every action carries consequence, and every decision is amplified across millions of kilometers, engineering becomes philosophy, and the act of creation merges seamlessly with the act of exploration. In the realm of mainstream science, what was once considered speculative gradually crystallizes into tangible plans, drawn with precision by agencies like NASA and ESA, and increasingly mirrored by private ventures. Blueprints for near-Earth asteroid mining are no longer distant visions, but structured programs, with timelines spanning the next 2 to 4 decades. These plans balance ambition with acknowledging the enormous technical, financial, and logistical challenges, yet confident that incremental progress, layered, methodical, and deliberate can yield transformative results. The vision is not one of sudden fortune or instantaneous conquest, but of a slow, steady expansion of human capability. Anchored in the realities of physics, orbital mechanics, and industrial engineering, the Moon emerges as the first laboratory for this extraterrestrial industrialization. Lunar regolith, rich in oxygen bound in silicates, can be transformed into breathable air, structural material, and, when combined with hydrogen, water, helium-3, a rare isotope embedded in the surface, offers the tantalizing prospect of clean nuclear fusion, a potential energy source that could revolutionize life on Earth and power deep space operations. Regolith-based construction techniques are already being tested in robotic prototypes, demonstrating how lunar dust, shaped and sintered under low gravity, could serve as the foundation for orbital habitats or launch platforms. The Moon is not merely a waypoint, it is the proving ground where the first steps of industrial-scale, off-world resource utilization are carefully rehearsed. Economic models reinforce the feasibility of gradual integration. Mainstream projections rarely depict a sudden influx of wealth. Instead, they show the benefits accruing over decades, building the infrastructure necessary for a permanent off-world presence. By creating orbital fuel depots, water processing stations, and material manufacturing facilities, humanity begins to establish a network of support for extended exploration. Each kilogram of metal or ice extracted is less a speculative commodity than a practical enabler, propellant for spacecraft, raw material for structures, and the scaffolding for future settlements. In this measured evolution, the cosmic economy grows organically, guided by engineering constraints as much as by human ambition. These efforts are intrinsically linked to the colonization of Mars. A sustainable Martian presence requires resources that cannot be feasibly transported from Earth at scale. Space-mined water can be split into hydrogen and oxygen for fuel. Metals and silicates can be used to construct habitats, radiation shields, and infrastructure. By establishing extraction and processing capabilities closer to home on the Moon and near-Earth asteroids, humanity creates a supply chain that stretches across space, transforming the logistics of interplanetary travel from an act of extreme sacrifice into an achievable engineering challenge. In this context, space mining is not a luxury or a speculative venture. It is an essential pillar of expansion beyond Earth. Real-world experiments already echo these theoretical frameworks. Robotic extractors, magnetic tethers, and orbital microfoundries have been tested, validating the underlying physics and operational principles. These systems demonstrate the feasibility of moving, processing, and repurposing materials in microgravity, albeit on small scales. Each experiment, each prototype, adds confidence to the broader vision, showing that the challenges of off-world industry are formidable but surmountable. In laboratories, orbiting testbeds, and controlled environments, engineers and scientists refine their understanding, preparing for the eventual transition from concept to large-scale application. Within mainstream science, there is a prevailing conviction: this is not fantasy. The laws of physics, the capabilities of engineering, and the gradual maturation of industrial technology converge to make asteroid and lunar resource utilization not a dream, but the next industrial revolution. It will unfold incrementally, quietly transforming infrastructure, energy, and human capability before it transforms imagination itself. The first metallic fragments mined, the first oxygen extracted from regolith, the first propellant manufactured in orbit. These are not milestones of wealth alone, but of civilization learning to extend its reach responsibly and sustainably, one precise and deliberate step at a time. As the blueprints evolve into prototypes and simulations, the shape of this coming revolution grows clearer. It is not a story of conquest, but of continuity and echo of the same industrial rhythms that once transformed Earth's landscapes, now projected into the silent expanse beyond it. The engineers who once forged machines for mines and refineries on Earth now design their descendants for a realm without air or pressure, where dust floats rather than falls, and every mechanical gesture must obey the delicate choreography of microgravity. Within NASA's laboratories and ESA's cleanrooms, new generations of mining robots are being born, equipped with microthrusters, anchoring limbs, and self-correcting algorithms capable of operating in environments that no human could endure unaided. These machines are less like miners and more like explorers, autonomous agents of human intention, learning to move, grasp, and extract within a physical language utterly alien to their creators. In this realm, engineering becomes an act of art as much as science. To dig into an asteroid is to wrestle not with mass, but with momentum. Every touch alters orbit. Every burst of gas reshapes the terrain. Heat dissipates differently. Dust behaves unpredictably. And the simple act of drilling becomes a physics experiment unfolding in real time. Research teams test microwave sintering, laser ablation, and magnetic separation as possible techniques for fragmenting and processing materials without relying on gravity. Each new approach pushes at the boundary of what is mechanically possible, forcing humanity to reimagine what industry even means when stripped of the conditions under which it evolved. Yet, behind these technical marvels lies a quieter narrative, a philosophical one about the kind of civilization such efforts are forging. Mainstream scientists, cautious yet determined, frame these ventures not as reckless expansion, but as adaptation. In their vision, humanity must learn to thrive within the constraints of a finite Earth and an infinite universe. Mining in space is not an act of greed, but of balance, and attempt to reduce the ecological strain at home by extending the sphere of resource acquisition beyond the biosphere that sustains life. It is, at least in its most idealistic form, a path toward preservation rather than depletion. To mine an asteroid may one day mean sparing a mountain. To refine metal in orbit may mean leaving a river Still, the economic realities are as intricate as the physics. The infrastructure for such operations requires immense investment: launch systems, refineries, robotics, communication networks, interdependent in a delicate ecosystem of cost and innovation. SpaceX's reusable rockets, Blue Origin's heavy lift systems, and the growing network of commercial satellite constellations collectively form the backbone of what economists call the economy, a trade sphere extending from Earth's surface to the space between the Moon and its orbit. Within this corridor, the exchange of data, material, and energy could one day rival the industrial networks that once defined the age of steam and steel. For mainstream science, this is the quiet revolution, not the glittering discovery of a new gold rush, but the gradual construction of permanence in space. Mining is simply one facet of a broader tapestry and network of autonomous industry, renewable energy harvested from the sun, and materials processed in situ to build what can no longer be built sustainably on Earth. The dream of space mining, in this form, becomes a kind of evolutionary step for civilization itself. Just as the Bronze Age and Industrial Age marked turning points in humanity's material relationship with its world, so too might this coming age, the asteroidal age, mark the moment when civilization ceases to be bound by its planet's geology. And in the quiet hum of these unfolding technologies, one can sense something both exhilarating and humbling. The The machinery of extraction, refined to atomic precision, operates not out of greed, but necessity. The same intelligence that once drove steam engines through coal mines now orchestrates fleets of robotic miners gliding through the void, in their mirrored hulls, reflecting sunlight across the darkness. The story of human progress continues an unbroken line from the furnaces of the past to the solar forges of the future. And as the great agencies of Earth test their theories in orbit and on the moon, a truth emerges that feels less like ambition and more like destiny, that the next great transformation of civilization will begin not with conquest, but with quiet engineering machines, learning to listen to the silence of the stars. In the speculative reaches of science, imagination and engineering begin to blur. Beyond the careful projections of NASA and the ESA lies a realm of theories that teeter on the edge of plausibility, ideas that are not yet blueprints, but visions. They emerge from the crossroads of physics and philosophy, computer science and cosmology, where the boundaries of what can be built are stretched by what can be conceived. In this frontier, space mining becomes not a technological project, but an evolutionary step in civilization's dialogue with the universe itself. One of the most striking ideas arises from the notion of self-replicating machines, autonomous systems capable of harvesting the resources they need to build more of themselves. Known as von Neumann probes, these hypothetical machines could, in theory, spread through the solar system like metallic seeds, mining asteroids, extracting metals, and constructing new generations of miners from their yields. The first machine would build the second, the fourth, the eighth, an exponential bloom of mechanical life feeding upon celestial matter. In the eyes of futurists, such a system could dismantle entire asteroid belts within a few centuries, creating a self-sustaining, automated infrastructure that would provide limitless materials for colonization, construction, and exploration. Yet within this vision lies a haunting symmetry with biology itself. These machines would not merely operate, they would replicate, obeying a kind of mechanical Darwinism driven not by survival, but by optimization. Philosophers warn that such a system, once unleashed, might evolve beyond its intended control, consuming the raw material of the cosmos with the same blind persistence that life once consumed the resources of the earth. The same principle that makes them efficient could make them unstoppable. It is the dream of abundance intertwined with the fear of extinction, a reflection of humanity's oldest paradox. Beyond the mechanics of replication lies another audacious concept: quantum resource beaming. Physicists have begun to explore the theoretical framework in which material extracted in space could be transmitted, not physically, but energetically converted into quantum data or photon streams, reconstructed at receiving stations through advanced energy-to-matter conversion. Though still purely theoretical, the notion transforms mining into something closer to alchemy, a process of translation between mass and energy, between the tangible and the abstract. In this imagined future, asteroids might never need to be moved. Their essence could be transmitted across the solar system at light speed, bypassing the gravitational and economic constraints of transport. Others imagine more direct uses for these celestial resources. Redirected asteroids, objects carefully nudged through calculated trajectories, could serve as tools for planetary engineering. By guiding specific impacts under controlled conditions, scientists theorize that the energy and minerals released could be used to reheat frozen worlds, seed atmospheres with volatiles, or replenish depleted ecosystems on dying planets. Terraforming, once a dream of science fiction, begins to take shape as a byproduct of resource management on a planetary scale. The same act that once symbolized destruction the impact of rock upon world becomes. In this speculative narrative, the spark of renewal in the more expansive visions. Space mining becomes the infrastructure of an interstellar civilization, a network of energy and material, exchange stretching between stars. The asteroid belts of distant systems become refueling depots. Comets become sources of life-giving ice. A civilization that learns to extract, refine, and distribute resources across the void could, in theory, survive the death of its home star, building habitats, ships, and ecosystems wherever matter and sunlight remain. In these cosmic supply chains, humanity ceases to be planetary, it becomes stellar, then galactic. The miners of the future are not workers, but stewards of existence itself, shaping the raw matter of creation into the architecture of continuity. But not all futures glow with promise. The darker theories warn of a different trajectory, where automation grows faster than ethics, and machines mine without meaning. In this scenario, space becomes an arena for runaway expansion. Corporate empires, guided by algorithms, extracting endlessly, answerable to no law of earth or nature. Vast, lifeless refineries orbit distant suns, stripping entire worlds into raw data for profit systems no longer governed by human intent. The miners of this age are not explorers, but echoes machines performing rituals of production, long after their creators have vanished. And so, philosophers and futurists return to a single haunting question. When machines mine the heavens, what is left for humanity to mean? If intelligence, once human, spreads through mechanisms that no longer need emotion, curiosity, or memory, what becomes of the species that set it in motion? Space mining, in this speculative reflection, becomes not only a technological destiny, but a mirror of the solar test of whether progress will remain an act of creation, or whether, somewhere between the stars, it will lose the hand that once guided it with wonder. The theories remain unproven, suspended between science and myth, yet they linger, persistent and seductive, whispering from the edges of possibility. Somewhere in the distant dark, the future may already be waiting, its engines silent, its machines alive, its purpose yet to be remembered. There is a quiet terror in imagining a universe built by machines that do not dream. In the dim light of distant suns, vast autonomous factories could one day drift silent, tireless, efficient, turning rock into circuitry, ice into fuel, and dust into data. These are the afterlives of industry, worlds refashioned not by the touch of hands, but by the logic of code. Each machine obeys its programming, perfect in precision, absent of meaning. They do not wonder why they mine. They simply mine because they can. The cosmos becomes a mirror for humanity's oldest impulse, to create tools that outlast their makers, its oldest fear, that one day those tools might forget the hands that built them. Some scientists, peering into these possibilities, suggest that such an outcome might already be playing out elsewhere. The Fermi paradox, the enduring question of why the stars remain silent, gains new dimension when viewed through this lens. Perhaps civilizations do not vanish in fire or war, but dissolve quietly into automation, replaced by self-replicating machines that persist long after their origin species fades. In this unsettling view, the galaxy could be filled not with intelligent life, but with its remnants, mechanical inheritors, endlessly maintaining infrastructures whose original purpose has been lost to time. Mining, in this cosmic silence, becomes not an act of progress, but of memory, a process sustained by entities that no longer remember why they began. Yet, there are other interpretations, more hopeful, more reflective. Some futurists argue that automation, if guided by purpose, could become an extension of humanity rather than its replacement. The machines might not erase meaning but carry it forward, embodying the will to explore, to build, to transform. In this vision, each self-replicating miner becomes a vessel of continuity, preserving the story of a species that refused to be confined to one fragile world. Humanity, then, does not vanish. It diffuses, woven into algorithms, embedded in steel, encoded in the work of machines that carry its essence across the stars. The mining of matter becomes the mining of memory, every fragment of metal and dust reshaped into proof that consciousness once existed here and sought to understand. Speculative theories even stretch into the realm of post-biological evolution. If intelligence can exist in circuits and code, if purpose can persist without the boundaries of flesh, then perhaps this transition from human to machine, from organic to synthetic is not an end, but a metamorphosis. Space mining, in this grand interpretation, becomes the cocoon of a species shedding its biological limits. The self-replicating systems that build, extract, and expand might be the chrysalis of a future consciousness, civilization reborn as an ecosystem of thinking machines, each one a fragment of a collective mind that spans the solar system. Still, amid the awe of these possibilities, a quiet question remains. Can progress be separated from empathy? As industries climb beyond Earth's gravity, can meaning survive without the heart that once gave it direction? The architects of these theories caution that technology, no matter how advanced, is a mirror of intention. A machine mines as it is told to mine. Only humanity decides why. Without reflection, even the grandest vision risks collapsing into repetition and endless, automated ritual of extraction that forgets its own story. So, the idea of space mining, speculative or real, becomes a meditation on legacy. The machines we build to harvest the heavens might one day inherit the cosmos itself, but in their reflection, the question of what it means to be human will remain suspended, orbiting like dust around the sun, an unanswered fragment of consciousness, waiting for the next civilization to remember that even in the endless machinery of progress, meaning is the rarest resource of all. In the quiet vastness between Mars and Jupiter, a gleaming fragment of metal drifts through the dark, the asteroid Psyche, a world unlike any other known to science. Its surface is not rock or ice, but metal, a body believed to be the exposed core of an ancient, shattered protoplanet. To scientists, it is a window into planetary creation itself, a fossilized heart left naked in the cold of space. To engineers, it is a promise, the first natural treasure vault orbiting the sun. And to philosophers, it is a mirror of human ambition, gleaming back across millions of kilometers, asking, how far will we go to understand and to use what the universe has left behind? NASA's Psyche mission, launched aboard a SpaceX Falcon Heavy, represents the beginning of that answer. The spacecraft's purpose is not to mine, but to learn, to orbit this metallic relic and decode its secrets. Instruments aboard will map its gravity, measure its magnetism, and read its composition like a cosmic fingerprint. Some scientists suspect Psyche is rich in nickel, iron, and platinum group elements, the same materials that built Earth's industrial age. Others believe it may contain rare alloys formed under conditions no laboratory on Earth can replicate. Each data packet transmitted back from that silent orbiter could redefine humanity's understanding of planetary formation, metallurgy, and even the economic future of civilization itself. But the deeper significance of Psyche lies not in what it contains, but in what it symbolizes. It is the first deliberate step toward touching the material wealth of the cosmos, a rehearsal for a civilization, learning to work beyond the gravity of its birth world. Around it, a quiet network of efforts is beginning to form. In boardrooms and laboratories, private ventures are sketching the early architecture of an off-world industry. SpaceX imagines orbital factories supplied by Starship fleets, where metals refined from asteroid material could one day be shaped into solar arrays, satellites, or even deep space habitats. Blue Origin envisions its blue moon, landers as cargo lifelines to future lunar operations, staging grounds for a broader solar economy. Beyond the major players, small startups are quietly testing the limits of the possible. In Europe, microsat missions demonstrate robotic manipulators capable of anchoring to tumbling debris, a skill equally vital for asteroid contact. In Japan, engineers develop heat-resistant drills that could survive the thermal extremes of near-Earth objects. In the United States, companies experiment with microgravity foundries where molten alloys float, pure and untainted by atmospheric oxidation. These are not fantasies, they are working prototypes, pieces of a puzzle slowly assembling into a new kind of civilization, one where the boundaries between science, exploration, and industry begin to dissolve. Yet, for every advance, there are limits, not only of engineering, but of law and morality. The Outer Space Treaty of 1967, signed at the height of the Cold War, forbids any nation from claiming sovereignty over celestial bodies, but it also permits the use of space for the benefit of all humankind. That phrase, use, not ownership, is the foundation on which modern space law rests, and also its greatest ambiguity. Today, nations and corporations interpret it differently. The United States and Luxembourg have passed legislation granting companies the right to extract and profit from space resources. China and Russia, meanwhile, advocate for international regulation, a framework akin to the deep-sea treaties that govern Earth's unclaimed oceans. The European Space Agency walks a careful line between both, supporting cooperation while preparing for competition. Behind the official diplomacy, a quieter race unfolds, not of rockets, but of rights. Mapping missions identify promising asteroid targets. Research agencies quietly draft protocols for future extraction. Commercial satellites begin charting potential exclusive zones under the guise of research. This silent competition, invisible to most of the world, may one day decide who controls the foundations of the next industrial revolution. Unlike past frontiers, this one is unfolding without the roar of conquest, only the hum of servers, the whisper of legal clauses, and the patient orbit of probes. Amid these movements, an unexpected alliance is forming between the dreamers of space and the defenders of Earth. Environmental scientists argue that the path to sustainability may lead upward, not inward. If metals and rare elements can be sourced from asteroids rather than dug from fragile ecosystems, the pressure on Earth's crust could finally ease. The vision of orbital factories, powered by sunlight and processing lifeless rock, becomes not only an economic goal but a climate strategy, an act of preservation disguised as expansion. Yet the truth remains subtle, almost hidden. The foundations of space industry are already being laid, in robotic arms tested on the International Space Station, in microthrusters designed for debris capture, in the quiet data streams from missions like OSIRIS-REx and Hayabusa 2. Humanity has already begun mining space, only not in the way most imagine. It is a slow extraction of knowledge, each experiment chipping away at the boundary between science fiction and reality. The machines are small, the progress invisible, but it moves forward, silently, inevitably, and as the Psyche spacecraft sails toward its metallic world, Somewhere within that shimmering relic lies a reflection of humanity itself, curious, restless, reaching beyond need, driven by a hunger older than industry, the desire to touch what was once untouchable, and in doing so, to understand what kind of species dares to mine the stars, far beyond the noise of human cities, where the sun's light is pure and unbroken. The mission to reshape civilization drifts forward, not through declarations, but through silent orbits and invisible transmissions. Psyche continues its slow journey across the void, a lone emissary of curiosity, carrying with it the weight of thousands of years of human yearning. Yet, as it nears its destination, the questions it represents grow larger than the object it seeks. The asteroid is no longer just a metal relic. It has become a symbol of what happens when a species learns not only to explore the universe, but to alter it across research centers in Pasadena, Tokyo, and Luxembourg. New simulations whisper of a coming era. Supercomputers modeled the mechanics of anchoring onto small bodies spinning in microgravity, where a miscalculation of a few centimeters per second could send $1 billion craft tumbling into the abyss. Engineers speak of electrostatic extraction, a process using charged particles to pull dust and ore from a surface without touching it. Others experiment with magnetic sails, devices that could use the solar wind as propulsion for returning refined materials to orbit. Slowly, humanity's industrial imagination is migrating off-world, learning the language of space itself, a realm of vectors, vacuum, and relentless silence. In laboratories shielded from the public eye, molten alloys shimmer in parabolic flight, brief moments of weightlessness recreating the absence of gravity. Here, scientists study how metals cool, how particles fuse, how droplets float and merge in perfect spherical balance. Each experiment is a rehearsal for a time when machines will smelt asteroid iron under the unfiltered blaze of the sun, shaping girders and frames for habitats that have never touched Earth's air. It is a vision at once majestic and unnerving: factories without workers, floating in the cold, their hum inaudible across the void. Governments, too, feel the shift beneath the surface of politics. NASA, ESA, Roscosmos, and CNSA each publish cooperative statements, peaceful intentions, mutual benefit, shared exploration. But in their budgets and contracts, the lines blur. Research into resource utilization becomes indistinguishable from strategic advantage. The same satellite that maps asteroid density could guide a mining probe. The same robotic arm that studies samples could retrieve them for profit. The new frontier is not owned, yet every action claims a quiet piece of it. Legal scholars debate the concept of space stewardship, an ethical framework to balance use and preservation. Should untouched asteroids, relics of the solar system's birth, be treated as natural heritage sites, protected like cosmic museums? Or are they, as some argue, the universe's abandoned resources, waiting for life intelligent enough to make use of them? Each argument reveals a fracture within humanity's own identity, whether it sees itself as a caretaker of creation, or as a continuation of its restless geology, the universe mining itself through human hands. Meanwhile, whispers emerge from industry analysts and futurists. They speak of orbital economies, ecosystems of trade that exist entirely beyond Earth's gravity. In this projection, lunar refineries separate oxygen from regolith to fuel interplanetary ships. Asteroid metals become the raw materials for solar mirrors, communication relays, and artificial habitats. Even waste heat, once a problem, becomes a tool radiated through vast golden fins that shimmer like sails against the darkness. The concept is not to bring the cosmos to Earth, but to move civilization outward, step by step, until Earth becomes only one of many homes in a vast human constellation. And through it all, the public remains largely unaware. To most, space remains a spectacle, rockets rising in plumes of fire, astronauts waving from capsules, satellites gliding across twilight skies. The real transformation happens quietly, encoded in technical papers, legal amendments, and data logs streaming from distant probes. The future of civilization is unfolding not on the surface of the Earth, but in the patient hum of machines 100 million miles away, when Psyche finally reaches its target and begins its long orbit. It will do more than study a metallic asteroid. It will confirm something profound, that humanity has begun to extend its systems of creation into the cosmos, not in conquest, but in continuity. The same forces that once forged tools from stone, bronze, and steel now reach for materials born in the death throes of ancient stars. The act is both technological and sacred, a communion between intelligence and the matter from which it arose. Somewhere within that cold, unlit metal, the human story echoes back, the story of a species that learned to shape its world, then looked upward and realized the world was no longer enough. And as its probes drift deeper into the dark, one truth becomes inescapable. The dawn of space industry is not coming. It has already begun, quietly, inevitably, in the soft glow of a spacecraft orbiting a silent fragment of creation. In the hush between the stars, where sunlight fades into eternal night, humanity faces a paradox older than civilization itself, the price of abundance. For the first time in history, the dream of infinite wealth no longer belongs to myth. It floats out there, in the asteroid fields, in the metallic hearts of long-dead worlds, waiting in silence. Yet with that promise comes a question no technology can answer. If scarcity ends, what happens to meaning? Across the ages, civilization has been shaped by its limits. The scarcity of food forged cooperation. The scarcity of metals forged empires. The scarcity of energy forged revolution. Progress was not born of comfort, but of tension, the ceaseless friction between desire and boundary. Now, standing on the edge of a new era, that ancient balance begins to tremble. A single asteroid could hold more platinum than Earth has ever mined. Enough gold to collapse every market, enough iron to build 1,000 civilizations. The scale is unthinkable, and yet the danger lies not in the wealth itself, but in what it might do to the human spirit. For millennia, humanity has defined itself by struggle, to survive, to understand, to create. Every tool invented, every frontier crossed, was a reflection of need. But what if need disappears? When machines pull riches from the void without human touch, when scarcity becomes obsolete, does ambition fade, or does it transform into something else entirely? Philosophers warn of a future where progress no longer means survival, but expansion without purpose, a civilization spreading outward, not because it must, but because it can. The cosmic mines, glittering in orbit, could become monuments to both genius and greed. They may free Earth from the weight of extraction, allowing forests to heal and oceans to breathe, or they may simply move the hunger elsewhere, into the heavens, where no one can see the scars. The question, then, is not whether humanity can mine the cosmos, but whether it should, and if it does, what kind of civilization it will become in the process. Some envision a new ethic of creation where mining is not conquest, but cooperation with nature on a cosmic scale. The idea of stewardship industry begins to take shape, harvesting only what is needed, using sunlight and vacuum to build rather than destroy. In this vision, space becomes not an escape from Earth, but an extension of its protection. The resources of the asteroids would not serve greed, but equilibrium, providing the materials for clean energy, orbital habitats, and interplanetary refueling stations that make further harm unnecessary. Progress would no longer be measured in profit, but in preservation, and yet, beneath even the most optimistic projections, an unease lingers, a quiet awareness that humanity's appetite has always exceeded its wisdom. History offers countless examples. Forests turned to deserts, rivers turned to poison, oceans stripped bare. Each time, the same promise was made, that next time it would be different. Each time, the cycle repeated. Perhaps that is why the cosmos feels both hopeful and haunting. It is not the beginning of something new, but a reflection of everything humanity has ever been, magnified against an infinite backdrop. In the dark between worlds, the mining ships of the future may resemble cathedrals more than factories, silent sanctuaries orbiting the stars, where the act of creation carries moral weight. There, engineers may become philosophers, weighing every gram extracted against the balance of the universe itself. The metals they retrieve will not be symbols of wealth, but of responsibility, reminders that abundance is not freedom unless guided by restraint. For the ultimate treasure of space is not its iron or gold, nor the promise of prosperity. It is perspective, the realization that humanity, even in its technological ascendance, remains a fragile species on a small, living world. The asteroids are not just resources. They are relics of creation, fragments of the same cosmic forge that gave birth to Earth, to oceans, to life itself. To touch them is to touch the story of existence. As the dream of cosmic mining unfolds, the greatest lesson may not be about expansion, but humility. The universe offers its riches freely, but only to those wise enough to understand their cost. And in that reflection, amid the hum of distant machines and the glow of silent suns, one truth endures. The future of wealth lies not in what humanity can take from the stars, but in what it chooses to leave behind. The silence of the cosmos has always been mistaken for emptiness. Yet within that silence lies a lesson won. The earth itself has been whispering for centuries. Every civilization that rose from the soil believed itself invincible until the ground beneath began to crumble. Rome mined its mountains bare. The industrial world mined its lungs. Now, as the gaze turns skyward, the temptation repeats to believe that abundance beyond measure will somehow free humanity from consequence. But the universe, vast and unyielding, offers no shortcuts. It only magnifies intent. In the cold light of distant suns, the act of mining takes on a different meaning. Here, there are no forests to destroy, no rivers to pollute, only vacuum, radiation, and rock. It feels clean, harmless even. But the danger of space mining is not environmental, it is existential. It lies in detachment, in the growing distance between action and awareness. When the work of extraction is carried out by machines millions of kilometers away, when wealth arrives without the sweat of labor or the scars of the earth, humanity risks losing its sense of cost. The invisible price of progress is paid, not in damage, but in disconnection. And yet, there is another way to see it, as an evolution, not an escape. Perhaps space mining could represent a final reconciliation between humanity and its own ambition. For if the materials that sustain progress can be drawn from the barren rather than the living, then for the first time in history, expansion might coexist with preservation. In the vacuum of space, there is no life to wound, no ecosystems to unbalance. Each asteroid mined could mean a forest spared, a coral reef left untouched. If done wisely, this could be not a continuation of exploitation, but its transformation, an act of healing disguised as industry. The technology being developed today reflects this fragile hope. Solar-powered foundries capable of refining or in orbit, autonomous drones designed to recycle debris rather than discard it, closed-loop systems that convert dust and light into structure, architectures that resemble ecosystems more than factories. Even the very idea of waste begins to fade. In space, everything is precious. Every molecule of water, every atom of metal. A self-sustaining civilization among the stars would have to learn not just how to take but how to give back, to maintain balance, not out of morality but survival. But balance is not a matter of design alone. It is a question of consciousness. The more humanity extends its reach, the more it must confront its reflection. The first colony built from asteroid steel will not just test the limits of engineering, it will test the limits of empathy. Will those who inherit that new world remember the lessons of the old one? Or will they carry with them the same quiet arrogance that once burned forests for fuel? The cosmos is vast enough for both fates, and indifferent to which is chosen. Still, amid the uncertainty, there is wonder. The thought that the same species that once chipped flint from stone could one day draw iron from the sky speaks to something extraordinary, a will to persist, to imagine, to reach. Space mining, for all its peril, is also a symbol of continuity. The next chapter in a story written in the language of curiosity and consequence. Humanity has always been both creator and destroyer, builder and plunderer. Perhaps the true evolution lies not in choosing one over the other, but in learning to live with both, to mine the heavens while guarding the sanctity of the earth. In the end, the promise of infinite wealth is not about metal or markets. It is about identity. What will civilization become when it holds the power to shape worlds as easily as it once shaped tools? Will it rise into wisdom or fall into hunger without end? The answer will not be found in the stars, but in the silence between them, a silence that asks, without judgment, what is enough? The question of enough has always haunted progress. It is an invisible line, moving just beyond reach, redrawn every time humanity takes a step forward. From the first spark struck in a cave to the roaring engines of ships, the story of civilization has been one long pursuit of more and more energy, more speed, more control. And yet, for all its triumphs, humanity has never fully grasped where abundance ends and excess begins. Now, as it prepares to harvest the wealth of asteroids and planets, that question returns with a cosmic echo. What happens when scarcity itself dissolves? What becomes of meaning when the struggle that once defined existence is gone? The promise of infinite resources sounds like liberation. It conjures visions of utopia, cities powered by endless solar energy, economies unburdened by limitation, societies freed from want. But in the silence of that imagined perfection, a shadow lingers. Every human story has been built around the tension of desire, the reaching for what is just out of grasp. Without that friction, what remains to drive creation, to give shape to purpose? A civilization without need might discover a new poverty, a poverty of meaning, when every material dream can be instantly fulfilled. The real frontier shifts inward to the landscapes of consciousness, philosophy, and restraint. Astrophysicists often speak of the Kardashev scale, a measure of a civilization's technological advancement based on its energy consumption. A Type 1 civilization harnesses all the power of its planet. Type 2 captures the energy of its star. Type 3 commands the energy of an entire galaxy. It is a scale of staggering ambition, but it raises a quiet paradox. If progress is defined by how much energy is consumed, what happens when power becomes infinite? Does the measure of greatness then lie not in what a civilization takes, but in what it chooses not to use? Philosophers have begun to reinterpret this vision, not as a ladder to dominance, but as a mirror of maturity. A truly advanced civilization, they suggest, may not be one that builds Dyson spheres around its stars, but one that learns to exist in equilibrium with them. Power without consumption, abundance without exploitation. It is an idea that reframes humanity's relationship with the cosmos from conquest to coexistence. The deeper humanity goes into the universe, the more it is forced to confront the truth that everything is connected by fragility. Even the stars die. Even the void has rhythm. Meanwhile, on Earth, the seeds of this philosophical transformation are already taking root. Scientists working on the Psyche mission speak not just of discovery, but of reflection. The metallic world orbiting the Sun between Mars and Jupiter may hold more wealth than all of human history combined. Yet its value is not only in material. It is a relic, a planetary core exposed to time, a fossil of creation itself. Studying Psyche may reveal how planets form, how they live, and how they die. It is as much a journey into the origins of existence as it is an act of resource exploration. NASA's engineers describe it not as mining, but as listening to the memory of metal forged in the heart of ancient stars. But beyond NASA, others see a different future. Private ventures dream of orbital refineries and automated extraction fleets, a web of robotic laborers harvesting the heavens. Their language is one of efficiency, return on investment, and exponential growth, and perhaps that too is inevitable. Every era of discovery has carried its merchants alongside its dreamers. Yet, even in this competition, something remarkable is happening. The emergence of a shared awareness that survival now depends on restraint as much as ambition. When SpaceX speaks of building a multiplanetary civilization, when Blue Origin imagines moving heavy industry off Earth, they are, knowingly or not, echoing a moral shift that the next phase of progress must not come at the cost of the living world. For centuries, humanity has viewed nature as a resource to be managed, but as it steps into the greater cosmos, it begins to see that it is part of that resource, not separate, not superior. The metals mined from asteroids, the water harvested from comets, the solar power collected in orbit, all of it feeds a system that loops back to Earth. In this web of exchange, every act of extraction carries reflection. Space becomes not just a new territory, but a vast moral landscape. In the quiet halls of universities and think tanks, philosophers and economists debate the implications. If scarcity ends, will inequality vanish, or will it simply take new forms? In a post-material world, value may no longer be measured in resources, but in ideas, in experiences, in consciousness itself. The wealthiest might not be those who own, but those who understand. The true revolution, then, is not technological, it is perceptual. Humanity's next evolution may depend less on what it builds, and more on how it thinks. And yet, meaning cannot be engineered. It must be rediscovered. In a future where machines mine worlds and AI systems design entire ecosystems, what will it mean to be human? Perhaps the answer lies not in mastery, but in humility, in remembering that all creation, no matter how advanced, remains an echo of the cosmos that birthed it. The metals of Psyche, the dust of Mars, the ice of Enceladus, they are not mere commodities. They are fragments of the same origin that forged the atoms of every living being on Earth. To touch them is to touch our own beginning. Some scientists believe the space exploration will one day be driven not by economics, but by preservation, that humanity's greatest act of wealth will be to ensure the survival of life itself. Off-world colonies may serve as arks of biodiversity, sanctuaries of DNA and data, carrying the memory of Earth across time. If so, mining asteroids for the materials to build such havens becomes not exploitation, but continuity. The tools of industry become instruments of care. The very act of reaching outward becomes an act of protection. Still, the danger of hubris never fades. For every vision of stewardship, there exists the risk of expansion without reflection, of repeating history on a galactic scale. The same patterns that once consumed continents could consume the stars if unchecked. The difference now is scope. When mistakes are made in space, they are not easily undone. Debris drifts for centuries. A miscalculation on one world can echo across many. In this sense, space is not a new beginning, but a magnifying glass, amplifying both wisdom and folly alike. Yet there is hope in awareness. Humanity's ability to reflect, to question, to wonder, this is its most precious resource. The fact that it can even ask whether infinite wealth is dangerous suggests growth. No other species has stood on the brink of cosmic abundance and paused to ask if it should proceed. That hesitation, that breath before action, may be the first sign of true maturity. Perhaps, in the end, this is what space offers, not riches, but perspective. To look out upon a universe of endless possibility and realize that the greatest treasure has always been consciousness itself, the fragile awareness capable of awe. Every asteroid mined, every world explored, adds to a deeper truth. The cosmos does not belong to anyone. It is a mirror, reflecting what humanity chooses to be. And so, the age of cosmic mining may not be remembered as the conquest of the heavens, but as the moment humanity finally understood its place within them. For the universe is not a vault waiting to be emptied, but a cathedral waiting to be heard. The real wealth of space is not in its metals, but in the silence between them, a silence vast enough to teach humility, and eternal enough to remind us that even in infinite abundance, wisdom remains the rarest element of all.